In this video, I'd like to talk about hierarchically decomposed graph convolution networks, or HD-GCN, for the task of skeleton-based action recognition, which is a paper published in ICCV 2023. But before talking about HD-GCN, let's just briefly talk about the main idea behind three popular methods that have been proposed before this one. The first GCN-based method for the task of skeleton-based action recognition is called ST-GCN, which is from AAAI 2018. That it simply tries to consider some graph structure based on human topology and apply graph convolutional networks on top of it. And for the temporal dimension, it just uses TCN. But an issue that we can say this sort of modeling has is that it always connects, for example, this elbow to this shoulder and to this wrist. But what if in a certain action we should pay attention to multiple different areas of the body, and for example, if I want to walk, then my wrist and my ankles are kind of correlated, because as I move my ankles, I also move the wrist as I walk. But the ST-GCN doesn't consider them, and it only passes the information from elbow to the wrist and nothing more. So researchers in CVPR 2020 proposed MSG3D, which is kinda an equivalent of 3D convolutions but in graphs instead. And what I mean is, for example, let's just focus on this black node. Previously, before this MSG3D, we only connect the adjacent nodes, which is this yellow node and this one, as just some neighbors, and pass the information from these yellow ones to this black one. But now they say, in addition to these yellow ones, we can also connect other ones that are further away, like this blue one that has distance of 2, or this red one that has distance of 3. And not only that, but we can also connect the joints in the next frames and the previous frames, but not on the whole frames and the whole joints for sure, only in the local area around this black node. But then in ICCV 2021, researchers have proposed CTR-GCN, or Channel-Wise Topology Refinement GCN, which essentially what it does is that it just defines some shared topology based on physically connected edges, and then they say each node is initially represented by three values, right? X and Y and Z. And what we do is that we use some matrix multiplication W that maps it from 3 dimension into a higher dimension like 64. Then they devise a method that for each sequence it dynamically assign a new sort of topology for each channel. Like for the first channel it assigns this topology, and on the last channel it assigns this topology, and then they refine the original shared physically connected topology with these topologies by simply adding them, which we end up having these sort of topologies in the last column. And now let's just talk about HD-GCN by first talking about hierarchically decomposed graph. So what they initially do in the paper is that they convert this graph structure of human body into a tree. But how can we do it? We definitely need a root for the tree. And for the root, they simply use center of mass, which could be center torso, or like bottom torso or upper torso. Let's just say we are using center torso for now. And the way that we construct tree is that we say center torso is our root, and since it is connected only to 2 edges, we say it has 2 children, which are upper torso and bottom torso. And this could be our first edge set. And for the second edge set, we further expand it and say upper torso is connected to neck, left shoulder and right shoulder, and bottom torso is connected to left hip and right hip. And we can do it over and over until we construct the overall tree. But note that it doesn't change anything. We just change the representation from graph into tree, and that's it. Later, as I will show, they define something on top of this tree just to make it perform better. So now let's just see how can we mathematically represent this tree. As you remember, in graph convolution networks, we need something called adjacency matrix, which shows which joints are connected to which joints. It used to be a matrix before, but now it is a tensor that is NL number of V times V matrices. So before it could be like 17 by 17, but now it is 4 times 17 by 17. Why 4? Because we are having 4 different edge sets. And to further elaborate it, let's just say for the first edge set, we have a matrix like this, which should represent which joints are connected to which joints. So in the first edge set, what nodes are the parents? Only one node, which is center torso. And what are the children's? Those are upper torso and bottom torso. So we just say for the row center torso to the columns of the bottom torso and upper torso, we should have entry of 1 because those are connected. But what about the other entries? Those are all 0. Note that it is a directed adjacency matrix, meaning that we only have centrifugal connections from the parent towards the children and not vice versa. You might say why, but just hold on, I will explain it. For the second matrix, we say what are the parents? Those are upper torso and bottom torso. And what about children? We can say for the bottom torso, it is connected to left hip and right hip, which is color-coded by blue. And for the upper torso, the children are neck and left shoulder and right shoulder, which are color-coded by green. And we can simply say, for example, for bottom torso, left hip and right hip should be 1. And for upper torso, neck and left shoulder and right shoulder should be 1. And all the other entries should be 0. I guess you get the idea for the third edge set and the fourth edge set. And mathematically we can say we have a couple of edge sets, those 4 sets that I just mentioned, that connect node set H1 to H2 and then H2 to H3 and finally H3 to H4. So what are these HI? Those are node sets. Don't mix those up with edge sets. Node sets means nodes that are in a certain depth of the tree. For example, center torso is in H1, upper torso and bottom torso is in H2, and all these nodes in H3, all these nodes in H4, and finally all these nodes in H5. But as you might have guessed, having a directed adjacency matrix is not a very efficient thing to do, because center torso always passes the information to upper torso and bottom torso. But how center torso is going to be updated? We don't have anything for it, right? But we should have. We need to have some centripetal sets, meaning some edge sets from the children towards the parents. So upper torso and bottom torso should pass some information towards the parents, which is the center torso, and this way we can update center torso. And also we need to have some identity edges from one node to itself just to preserve the information it already has. So we can define this bidirectional adjacency matrix that looks like this. It is an edge set but composed from 3 different subsets. The first one is identity edges, which as I said just connects one node to itself. The second one is actually centrifugal, that they made a typo in the paper and called it CP, which stands for centripetal. And the last one is actually centripetal, that connects children to the parents. And once we have these 3 different subsets, then we can represent adjacency matrix by this 4-dimensional tensor, which says I have NL edge sets, I have 4 edge sets. Each edge set has 3 subsets. What are these subsets? Identity subsets, which is connecting one node to itself, centripetal, which connects from the node itself to the parent, and centrifugal, which connects from itself towards the children. And for each of them, we are having this V times V matrix, which says which node should be connected to which joint. And this way, we hierarchically decompose the graph into a tree. But now you might ask yourself, why do we bother myself this much? What's the point? Well, once we can define this tree, we can define a new set of connections, which are these fully connected connections, which is actually what is implemented in HD-GCN, that for each parent, in addition to the children of itself, it has some sort of connections to other children's that they belong to other parents. So, for example, this bottom torso is also connected to left shoulder and right shoulder and neck, which originally we don't have any sort of these connections, but now we have. And that's a sort of new sort of connections that they defined in this paper. But that's not the only contribution of this paper, and we need to see how they apply graph convolutions. They defined this module as HD graph convolution on KS hierarchy set. And remember, we had 4 different edge sets, and that means for each of these edge sets, we need to have this module. That as the input, it receives a tensor X, which is the original sequence that we have. It is having T frames, V joint, and each joint in each frame is represented by a C-dimensional vector. So initially it is 3, then they map it into 64, and then 128, and in the last few layers it is 256. So let's just assume this C is 64 for now. The thing that they do is that they have this phi function that is just some weight matrix multiplication that maps each node in each time frame from C-dimensional vector into C divided by 4. Why they do a C divided by 4? Because we have 4 branches. They wanted to apply 4 different sort of operations and then finally concatenate them again to be C-dimensional again. And how do they do it? For the first 3 branches, they just do graph convolutions. They say we have 3 different subsets for adjacency matrix in the KS hierarchy set, which are centrifugal from parent to children, identity from one node to itself, and centripetal from children to the parent. And for each of these, they define a unique sort of weights, which is kind of different compared to what we had in the original graph convolutions. So if you remember from graph convolutions, after multiplying the input tensor by this adjacency matrix, we multiply it by some weight, which is in this case theta. And this theta should be made of different sort of kernels that each kernel should say, for example, first channel is more important than the second channel, and another kernel says second channel is more important than the first channel, and they gather different sort of features. But once we separate them into centrifugal and identity and centripetal, that means for different sort of edges that we have, we are learning at different sort of weights. And that means if I want to pass some message from center torso, which was the parent, towards the upper torso and bottom torso, which were the children, I have one unique sort of weights. But when I wanted to do the vice versa thing from the children towards the parent, I have different sort of weights. That is something we didn't have before. And now it is more flexible to learn different sets of features. But that's not the only thing. What about the 4th branch? They utilize a module called edge convolution. And the way that this edge convolution works is that we initially have C times T times V tensor, right? We do the average pulling over T dimension, which ends up giving us C times V. Or in other words, it looks at one single joint, for example, neck, at 64 different time frames, and then take the average of all these 64 time frames, and we end up having a single node of the neck, which is representative of the whole sequence. So instead of having 64 frames, now we have only a single frame representing the whole sequence. But once we have this, instead of having those physically connected edge sets from, for example, center torso towards upper torso and bottom torso, now they say, let's the model decide that based on the sequence that it receives as the input. But how can it decide that? We can use one simple operation, which is k nearest neighbor. How this KNN should work? Well, we can say as the input, we have, for example, 17 different joints. Each joint is represented by c-dimensional vector. So we have 17 different vectors. And we can use the similarities between these 17 different vectors just to have some connections. By having some connections from a vector to the most similar vectors that have the least distance, which we can visually see here that the red node is connected to the 5 nodes that are the closest compared to the others. And those nodes pass the information to this node that we have at the center. And this is for the adjacency matrix, and then we have some W edge, which does the exact graph convolution thing. And once we have the output of these 4 branches, we just concatenate them and have this C prime times T times V. Why denote it C prime, not C? Because at some point during the middle of the neural network, they upsample the number of channels from, for example, 64 to 128. So in those cases, C prime is bigger than C, but in other cases, it is equal to C. And for sure, in those cases, we do downsampling in temporal dimension. Instead of 64, we are having like 32 instead. Okay, so how can I mathematically represent this module? I can say I have this equation for the first 3 branches that says for each subset S, which was identity, centrifugal, and centripetal, we apply this graph convolution. How do we do it? We say we have adjacency matrix for the K hierarchy set. How many hierarchy do we have? We have 4, because we have 4 edge sets. And for each of them, we look at the one that corresponds to this subset S, and we select that adjacency matrix. And for the input fin, we pass it to the function phi, which is some matrix multiplication that maps from C dimension into C over 4. And what about the last one? That is theta. And as I said, it is made of different sort of kernels. That first kernel says some channels are more important than the others. The other kernel says some other channels are more important than the others, and learn some features. And once we do it for all these 3 different branches, we connect them all together. And what about the last one? Here they represent it this way, that we just have this Fn as the input, pass it to this phi again, just to map it to a lower channel dimension, and then we do the average pooling over the temporal dimension to have a single frame representing the whole sequence. And then we have this function ZV, which is this edge convolution that I just explained. And finally, we concatenate them again. So we do it for edge set 1 and 2 and 3 and 4. And finally, we sum all these things together to have the final output. Why do we sum these things, you might wonder? Here in the paper, they say because different data sets have different number of joints. One can have 17 while the other can have 25. And having different number of joints means they cover different areas of the body. Like some can cover ears and eyes while others do not. And if you cover more area of the body, that means you're having more edge sets. Sometimes in some, depending on the data set, you might end up getting 4 edge sets, while in the others you might end up getting 5 edge sets. And if we concatenate the here instead of sum, that means based on the data set, we are changing the model structure, which is not an ideal thing to do. And by taking the sum instead of the concatenation, we always end up having the same architecture for this neural network. Hope it makes sense. And yeah, this should be the initial idea of how can we apply this graph convolution. But then they said, why do we do sum here? Can we do weighted sum instead? Have some weights for each edge set? Actually, that's a better idea, right? Because one edge set could be more important than the other edge set in some sequences, while in other sequences, the other edge sets might be more important. Who knows? I mean, it kind of makes sense, right? Because in different sort of actions that we perform, we are utilizing different area of the body. And based on that, some edge sets might be more important than the others. But how can we make a model define some weights based on the input sequence? They defined this attention-guided hierarchy aggregation. In this AHA module, what they do is they say initially we have a set of HD graph convolutions. Like this F1 is actually 4 different branches and then a concatenation of them, which results this F1. And likewise in all the others until we reach F and L, which in our case is just F4, right? So they say instead of taking their sum, we can concatenate them all initially and then take their weighted average. But why they do concatenation? What's the purpose? It's because of this AHA module, or this attention-guided hierarchy aggregation, which what it does is just initially just some max pooling over t dimension again, and then this RSAP module, which is representative spatial average pooling. And when we look at what it does, initially we have this tensor. So instead of taking the sum, if we concatenate, we are having C times NL. NL because of doing this concatenation, and then T and V again. But this RSAP, what it does, it looks at sets of nodes that we have in a certain edge set. So the union of HK and HK plus 1 is one edge set. So you can see here, for example, if we combine H1, which is this center torso, and H2, which is upper torso and bottom torso, we have all the nodes in edge set 1. And once we have it, the thing that we do is, for each node in the edge set, we take the maximum over all the values it has in the temporal sequence. So this center torso, as I said, has 64 different values because it has 64 temporal dimensions, temporal frames. And we take the maximum of all these 64 vectors, and we end up having a single vector for the center torso, which represents what it is in the whole sequence. And we do the same thing for the upper torso and bottom torso, and we have 3 different vectors that belong to this edge set 1. And once we have them, we sum all these 3 vectors and divide by the number of nodes that we have, which is 3. And that would be a single vector representing this edge set. And we do this for the other sets like set 2 and set 3 and set 4. And finally, we have 4 different vectors representing each set. And we want to kind of consider these vectors as our weights. But you might have thought that weights are just some scalar values, but they are not. They are vectors, and that means each channel has a certain weight. To further elaborate it, the thing that they do on top of this RSAP, they use edge convolution again. So they have 4 different vectors, they do the KNN, they select some subset of them and connect them together and pass some information, and finally have some weights. Why they consider them as weights? Because when you look at this formula, this is what happens. Let's just review it again. Initially, we have FHD of the K set. we pass it to the psi function, which what it does is this RSAV thing, and having a single vector representing the whole edge set, and we concatenate them for different layers that we have in the edge sets. We have 4 edge sets, so we have 4 nodes. And once we have 4 nodes, we pass it to this ZL, which is this edge convolution, pass some information to the closest ones, and then we finally having 4 vectors again for this 4 edge sets. And finally, they pass it to this sigma, which is sigmoid. And we know that the output of sigmoid is a value between 0 and 1, which we can kind of consider as some weights. And to show you in an example, let's just say the set 1 after passing all this RSAP and edge convolution is a vector like this, the weight that represents for the set 1. And for the last layer, which was the 4th one, or let's just call it NL as it is shown in this figure on the left, we have some vector like this. What they do is this operation here, which does element-wise multiplication with the tensor that we have initially. And that means this F1 for the first channel would be multiplied by 0.1, but FNL for the first channel would be multiplied by 0.5, and then we sum them together. In other words, in first channel, FNL plays a more important role than F1. But in the second channel, F1 would be multiplied by 0.8, but FNL would be multiplied by 0.3. Or in other words, F1 plays a more important role. Or in the last channel, channel 64, both have 0.2 as the weight, or in other words, they're having equal importance. And yeah, that's the way that they do. And that's all that it is in HD-GCN main operations. And next, just to further improve it, they do 6-way ensemble. This is way easier than before. They say when we have some graph of a person, we can represent them in kind of 4 different ways. The first way is just by storing the value of the joints. The other way is taking the distances of 2 adjacent nodes and storing that vector as a bone. And the other one is joint motion. So we have joint at frame 1 and joint at frame 2. We can kind of consider the distance of it as, and kind of consider them as a joint motion. And similarly, we can do it for the bone motion. And once we have these 4 different representations of the same skeleton, there is a paper actually called ST-GCN, or multi-stream attention-enhanced adaptive graph convolution networks, from year 2019, which uses all these 4 different representations as the input to further improve the accuracy of the model. But if you read it, you will see that joint motions and bone motions are not as effective as joint and bone. So here in this paper, they say, let's just select only joint and bone. And these are 2 ensembles. How can we make it 6-way ensemble? We can define different center of mass. Remember the root of the 3 center of mass, it was center torso, right? We can define one time to be the upper torso here, the other time to be belly or the center torso, and the other time hip or the bottom torso. And once we have these different center of mass, we are having different tree structures, which learns the different sets of things. So they say we come up with 2 different inputs, joint and bones, and for each of them, we are having 3 different center of mass. So 2 times 3, we are having 6 different sort of models. And we have all of them, we do the majority voting on their outputs, and that's our final output. And what about the network architecture? They say we have this skeleton sequence, and then it goes to HD-GCN, which is made of 9 different blocks. And the first block is HD graph convolution, the thing that we saw, followed by attention guided hierarchical aggregation, followed by temporal convolution. And about the number of channels in these 9 blocks, they just say that MSAA-GCN paper is our baseline. They have used these number of channels, so we are doing the same thing. And what about the temporal convolution? They just use the idea that CTR-GCN had, if you read that paper. And in CTR-GCN, instead of having a single temporal convolution, they have 4 different branches. Like you see, the branch on the left has 5x1 convolution with dilation of 1. But the other one has the dilation of 2, which means it skips one joint in the middle and has larger receptive field size. And the first branch has max pooling instead, and final branch has only 1x1 convolution. And then concatenate them all together and do the rest of the thing. And yeah, that's the main idea behind HD-GCN. And about the comparison of the model with the other models, we can see HD-GCN, if we do 6-way ensemble, it receives kind of 0.4% better accuracy in NTU RGBD in case of cross-subject analysis. And cross-subject means the training and tests are having different subjects, and cross-view means the train and tests are having the same subjects but in different camera views. So we can see in cross-subject is 0.4% better, and in cross-view it is only 0.1% better. And in NTU RGB 120, which has double number of actions, it is getting like 0.3% better in cross-subject and 0.4% better in cross-set. But what is interesting to me is even with this sort of very complicated architecture that they proposed, in kinetics skeleton, they are getting like 40.9% accuracy. While if you use this kinetics skeleton, but with the videos instead, with the RGB videos instead of the skeletons, we are getting 70%. So what's the gap, you think? There are many reasons, obviously. One reason could be when we are using skeletons, we don't have any information about the context, like when someone is writing versus when someone typing with keyboard. The skeleton pose might be kind of similar, while when we have the RGB video, we see that the laptop is in front of the person, and so it is easier for us to predict that action as typing instead of writing. But the other reason, which I believe might be the reason behind it, is the way that they pre-processed this kinetics skeleton. So if I remember correctly, they downloaded a lot of videos from YouTube, and then they used OpenPose just to predict some skeletons from the people within that video. But there are some videos that there are more than 2 people. And for selecting only 2 people, they say we select the ones with the highest confidence score. And selecting the one with highest confidence score, I don't think it's a very good idea, because what if during the middle of the video someone goes outside and another person comes in, and then the new person has a best confidence score, and that might affect kind of the action that's performing, because that's a completely new person and the action is different. I don't know. I mean, what if the person during the middle of the video, the confidence score changes from one person to another? Then we are tracking a different person, right? And I don't think that's a very reasonable thing to do. Maybe some tracking algorithm would be better. We are having a lot of them recently that they are actually robust to any occlusions and other things. I mean, without considering the ID switching which might happen, which I think in this kinetics skeleton, instead of developing all these complicated models, someone should come and does some sort of data engineering thing, just to come up with a better data rather than a better model and further improve it. Who knows, it might happen. But that's it. I hope you enjoyed this video. If you like it, don't forget to like and subscribe. And until the next video, goodbye.